All right, so reviewing how to find the domain of a function. For this first one, we'll start with a function that has a square root applied. We'll let f of x equal the square root of 3x plus 5. If you think back to kind of our checklist here for finding a domain, what we usually do with domains is we go into the problem thinking that the domain for the problem is going to be all real numbers. Remember, domain describes what x can be, or if I take those x values, I plug in the function, I get a real result back. So we go into the problem assuming the domain is going to be all reals. What we look out for, which usually gives us extra stuff to do, is we look out for restrictions. We see any little inequality statements that follow the function over here. If we see any intervals that follow the function, those sorts of things, that is your domain right there. Other things, we look for even roots. If you have even roots, you can only apply an even root to something that's positive or something that's 0. And then the last thing on that checklist would be if there's a rational function. If you've got like a denominator that's got some x stuff floating around in it. You can't divide by 0, so usually you do something with that denominator. You set that not equal to 0 and solve for x. So here we've got an even root, right? Specifically, we've got a square root. The stuff under the square root, that's the part we take out, and we set that greater than or equal to 0 because we can't take the square root of something negative. If we solve for x here, subtract 5 over, divide by 3. What we find is that it's okay if we take x values that are larger than negative 5/3, plug those back into the function, because if we do, we'll get real answers back. Therefore, our domain here, our domain, if we use interval notation, is going to be negative 5/3, and that's included, so we'll use the bracket, traveling up to infinity, because we're talking about values that are greater than negative 5/3. That's your domain for the first one. All right, second one here. Let's let our function be a quadratic on this one. F of x equals x squared plus 7. So think about that checklist I was just summarizing. You're looking for things like intervals or inequality statements that follow the function. You're looking for even roots. You're looking for denominators that have x's floating around in there. Do we see any of those things on this problem? I don't see any of those things, right? So if we go into these problems assuming the domain is going to be all real numbers, unless we see one of those three things I just described, for this problem, we don't see any of those three things. Domain has to be all real numbers. We can plug in anything we want for x. We'll always get a real result back. So that's a pretty easy one. All right, speaking of denominators that have x's floating around in them, let's try a rational function. F of x equals 1 over 3x squared minus 12. You got a rational function, you got x's floating around in the denominator. You can't divide by 0. So you take that expression that represents the denominator, you set that not equal to 0, and you solve for x. And solving for x here, you could slide the 12 over, divide by 3. When you take the square root of each side, we remember how there's a plus or minus. So a plus or minus square root of 4 would be plus or minus 2. What this is telling us is it's telling us x cannot be 2 or negative 2, but it can be anything else. So how we list the domain for this one, if it can be everything else, this is where we have some unions that are formed, right? We've got negative infinity all the way up to negative 2, which would be the lesser of the two values here that we found. You can't include negative 2, right? Because x can't equal that. We'd form a union with And let's see, there's -2 then up to 2, the next value that we found. Once again, can't include that other 2. Form a union with everything larger than 2, right? Oh yeah? So remember how interval notation works, right? Interval notation is describing basically your solution set if you illustrate it on a number line. If we find that -2 and 2 don't work, we open these up, but we include everything else. So you wonder where these intervals ever come from. You've got one interval here, a second interval here, a third interval here, right? Because here's your negative infinity to -2, here's your -2 to 2, here's your 2 to infinity. All right, what's the domain then? If our function equals the cube root of x squared minus 81. What's the domain? Yeah, we see a root, and we get in that habit with roots of taking this part out and setting it greater than or equal to 0. But when are we supposed to do that? If this is an even root, right? So if that's an odd root, domain, it's just going to be all reals. It's okay for that stuff under the root to be positive or negative because you can take the cube root of positive or negative stuff and even 0. So yeah, domain's all reals here because it's an odd root. So let's set up a similar function here on number 5. This time, though, we'll do the square root of x squared minus 81. So this time, with the square root being an even root, we will take this expression under the root out, and we will set it greater than or equal to 0. But now here's the kicker. We set up an inequality here that is not linear, like that first one we did. You got this quadratic instead. So if you have the instinct to move the 81 over, take the square root of each side, not going to work. Because remember, taking that square root of each side involves plus or minus stuff. So that involves a sign change, meaning we don't know exactly what to do with that inequality symbol when that sign change occurs. Instead, what we do, since everything's compared to 0 already, is we factor things out. Got a difference of 2 squares. And then we pretend for a moment with the factors we've got that we're solving an equation, and we find what are known as critical values. These are the values where this would all be equal to 0. The critical values here would be when x equals, from the first factor, 9, from the second factor, -9. These critical values kind of help set a little boundary for us for how the intervals might look in our answer. Then what we do, at least one way to do this, we set up a little chart and call it a 1-2 chart. On that chart, we have a column over here on the left, always designated for the x's. And on the right, we take this little factorization that was formed. X minus 9, x plus 9. And what we do is we go through and set up some intervals for these x's, potential intervals that could provide us with our answer for the domain. And we start at -infinity, and we work our way up to whatever the smallest critical value is, so -9. And sometimes we note what happens here at -9. Of course, at -9, what happens is this expression over here equals 0. Right? That's how we found -9 in the first place. But then we continue with the intervals. We go from -9 up to 9, since 9 is the next critical value stop. Could pause at 9, acknowledge what happens. Again, we get 0 back. That's how we got 9 in the first place. And then we continue onward up to infinity. to figure out what your domain is ultimately going to be down here. We know that negative 9 and 9 will be included. We know that because it's greater than or equal to 0. So this negative 9 where it's 0, this 9 where it's 0, we want that. We've got to figure out which of these intervals we can also include with this domain. So what we do, if I start with this interval right here, I pick a number on that interval, something less than negative 9, negative 10. I take negative 10 and I plug it in to this expression. All I care about is the sign that I get back on the answer. Because if I'm trying to find something that's greater than or equal to 0, I want positive stuff. So if I get a positive result over here in this column, I'm going to take those results, use that to form my domain. So negative 10 goes in. You got negative 10 minus 9, negative 19. You got negative 10 plus 9, negative 1. If you multiply a negative times a negative, you get a positive. So this positive is a good thing. If it's greater than or equal to 0, we want positive stuff. So part of my domain is negative infinity to negative 9, since this first interval worked. And as I said before, negative 9 can be included because of the whole greater than or equal to aspect. Now, if you're doing these problems correctly with quadratics, what ends up happening with these sign results is they rotate through, and you could check this, but this should be negative, this should be positive if we're doing this correctly. We don't want the negative, but we do want the other positive, meaning we'll form a union over here. When you form your union over here, that interval's from 9 to infinity. You can include 9, but that would complete my domain for the original function. All this extra work because you got a quadratic back here as an inequality. All right, for this last one, we're going to combine a couple of the ideas we've been discussing here. Let's take a rational function. Let's throw a root on top of x plus 8. And in the denominator, let's put x squared minus 4x plus 4. Got a couple ideas coming together. Since we have a root, we'll follow our rule for how to handle even roots. Take that expression of x plus 8 out, set it greater than or equal to 0, and solve. In this case, x is greater than or equal to negative 8. Now, take your denominator, use the rule for how we normally handle denominators. We take that expression, we set that not equal to 0, and we solve. Here with the quadratic, some factoring is involved. In fact, this should work out to be a perfect square because we get the same factors. We'll have minus 2 minus 2. So x basically cannot be 2. Whenever you have kind of a 2-for-1 in a problem, what I would encourage you to do is I'd encourage you to set up a number line and map out your two solutions here. Because where these intersect, or where they overlap on the number line, that's going to be your domain. So starting with the x is greater than or equal to negative 8. If that's negative 8, x is supposed to be greater than or equal to negative 8. We could include negative 8 and then shade over here. That's what that piece would look like. And then for the x is not equal to 2, well, 2 would have to fall somewhere over here. If it's not going to equal 2, we're going to open this up. Now, with regards to just this part, we could include everything else, right? If we're just looking at that part. In fact, we could include that 8, or that negative 8. The thing, once again, is you're taking the intersection of the two, so where do those overlap? Well, it looks like they overlap in here, right? The exception would be right here at 2. There's no overlap. So we've got a piece from -8 to 2, and we've got a piece from 2 to infinity, where this stuff is all coming together. Our domain would be -8, which we can include, up to 2, which apparently we cannot, form a union with 2 to infinity. Pick a number on those intervals, plug back into the function, you should get some real results.